Fun times are over. I want to remind you that when we talk about gravitational potential energy, we're no longer talking just about the difference between two places in a uniform gravitational field. Sometimes you have to look at a different way of calculating gravitational potential energy. This is this is an absolute amount because we are basing it relative to a place where the object has no energy, which is why it has more real value. But let's also understand that you can't use that like to measure or compare two places on the Earth's surface, because R doesn't change enough for it to be a reasonable way to do so, right? So if I'm saying I want to compare, say, the top of Mount Everest to sea level, although that feels like a big change to us, does the R in that denominator change very much? So it really isn't great if we're looking at something like that. It helps us maybe compare the amount of energy between being on the surface of the Earth and being in an orbit. And that's where we begin to see the relevance of using a function like that. So let's consider and I hate to keep going back to planet versus satellite, but there's just only so many ways to kind of talk about these things. So let's use this example first. If you have an object that's on the surface of the Earth, and it is important to be careful about where we talk about this being on the Earth. I mean, being here at Florida, you have a different amount of kinetic energy than, say, if you were at one of the poles, because we already calculated that we're moving pretty fast right here, aren't we? And so even though we say at that point is stationary, there's probably a combination of kinetic energy and potential energy associated with being at this location on the Earth. The value for potential energy, again, is measured from going someplace at infinity and coming up to, say, the surface of the Earth. But 0 is at the center of the Earth. So when we talk about this, a value for potential energy, it's relevant only to a specific object, because it's already been pre-calculated to start us at infinity and bring us close to one object. So that'd say, in this case, be the mass of the planet, mass of the satellite, g, and the separation distance. And don't forget, this value is negative. Now, we talked on Friday that we could use this to figure out what the escape velocity is. The escape velocity is whatever kinetic energy it takes to bring our total energy to 0. That would take us away from the Earth or away from our gravity well and place us far enough away where the force of gravity from all of those objects wouldn't be enough to pull us back. But the force of gravity would go to 0. And we also talked about the perhaps unrealistic idea that you could go someplace in the universe where that would be true, right? As soon as we get outside the Earth's gravitational pull, we're then contending with the sun's gravitational pull. When we get outside the sun's, then we might be dealing with the gravitational pull of our solar system. So the idea is to use this as a point of relative comparitance, meaning I could compare the total energy I would have, say, on the surface of the Earth with the total energy it might take to be in a circular orbit. If I compare these two, then I'm beginning to get some relative change in the amount of energy in those two locations. In fact, I'm pretty sure that the amount of energy I'd have here in orbit would probably be higher than the amount of energy I have at rest on the surface, because I'm going to increase my velocity a lot. And that's probably going to increase my total amount of energy. But, and this part's important, it doesn't matter whether I'm here at rest on the Earth or here in orbit where I'm traveling really fast, my total energy is still going to be negative in both locations. It has to be negative, because we already know that it takes the escape velocity worth of velocity to get us out from that gravity well. And that just brings us to 0 energy. So as long as we are trapped around a planet and being in orbit is being trapped, your energies are always going to be negative values. The difference is this one is going to be a smaller negative number than this one. And that difference would represent how much energy you would need to get into orbit. Yes, sir?
Why would the potential energy, why would the energies always be negative?
We already indicated that in order for us to escape the gravity well, to have enough velocity to escape, just doing that brings our energy to zero. Well, being in orbit means you're still trapped. You haven't escaped. So your total energy is still negative. You don't have enough kinetic energy to bring you to zero.
So we're doing it like relative to like a point in space rather than on Earth? Is that?
How about we do an example? Okay. You're welcome. We'll do 2 examples. And I'm going to count on you guys to be shockingly better than my 6th period, who said, I have no idea what you're doing, Mr. Shelton. Of course, that person had missed like 3 days last week. I was not shockingly condescending. I was ferociously condescending. Let's do this. Let's not worry about the spin of the Earth. That just adds complication. Let's just say we have an object sitting at the pole where it has no velocity, okay? And we're going to put it in orbit. And we want to do a relative comparison. So this isn't the Earth. This is some chunk of rock that has a radius of, say, r. And let's say that we want to go to a circular orbit that is 3r between the center of the planet and the orbit. So this might require a few steps to do what I'm going to ask. So let's say that step number 1, find the total potential energy of the object as it sits on the North Pole. That one's super easy. Let's say we have mass of the planet is MP and mass of the object is MO for object. What is the total potential energy for the object as it sits at the North Pole? Edward, what would be the expression for the potential energy on the surface? Negative MP MOG over R. Excellent. So that's how much energy we have, because we have no kinetic energy at that point. We're saying we're on the pole, so we're not moving. So now we give this object energy, and we get it into a circular orbit located at a distance 3r from the center of the planet. Find the total energy of the satellite. Understand, you're going to have to find an expression for V first. Your answer can have MP, MO, and R in it, and any fundamental constants that you want. But again, to do this, you will have to find an expression for V. And we've done this already, but you're going to look at me as if we haven't, and then say, I don't know where to begin, Mr. Shelton. Newton's second law. Start there. And I'll call on one of you, especially one of you who will be shocked by me calling on you. But I'll do my best not to be condescending. It's like you guys go off for the weekend, and then when you come back, it just doesn't come together. It's not much. There's not much here. I even said to start with net force equals MA. Good place to start. What's the force that's pulling on the object? Gravity. M for MP, MO, G over how far apart are they? 3r squared equals M. What is the M here? What's the thing that's in orbit? So we put O here. That's good. And then V squared over R. V squared over, which R do we put here? Is it R or 3R? Or something different altogether? It's the radius of curvature. Can you tell which circle? Is it going through the big white circle or is it going through the blue circle? The white circle. What's the radius of the white circle? Shockingly condescending. Not much here, by the way. This will not be the answer. This just tells you how fast it's going. Something we did before. Before we did something like 2 pi r equals v times t because we were interested in the period. I am not interested in the period right now. I could be, but I'm not. What does this give you? It gives you velocity. It's important. Why? Because I asked you to calculate the total energy of the object in orbit. What kinds of energy will the object have when it's in orbit? I think since we have linear velocity, we'll probably just do translational. We could convert this to an angular velocity. We then have to do the moment of inertia of the planet or satellite. How about we just do translational since we have v? So yes, it's going to have, if I want to calculate the total energy, it's going to have kinetic energy and it's going to have potential energy, and that's where we begin. Kinetic energy, 1/2 mass of object, v squared. Right, Allie? Allie's looking bored. She's like, yeah, I know. What do I subtract here, Allie? I would subtract the gravitational potential energy because it is indeed negative. And what would it be? Yes, it would. So when I subtract these, can you see that it's going to be negative? I'm afraid that not all of you can, which is why I'm going to go one more step, which brings me not a lot of happiness, but at least contentment. Can these two things be combined in some way? Sure can. How would I do so? What's that? It's how fractions work, I know. It's called something here. It's pretty easy. Thank you. Hey, you say it like that, but I'm looking at some people who were not convinced. So there we go. Common denominators, which is going to give me, as I said before, a negative number, MPMOG over 3R. This will be the total energy of the system when it's in orbit. 6R. 6R. More or less energy than it had here. I mean, you have to compare these. And I know they're both negative, but the original amount of energy was negative MPMOG over R. The new amount of energy has a 6 in the denominator, making this number smaller, right? Closer to 0. So it has more energy as we get closer to 0. In fact, if we subtract these, that tells you how much energy you would have to add to the spacecraft in order for it to reach this orbit. That's how you figure out how much fuel you're going to need. All of that kind of stuff. This is why launching from the equator makes a difference, because you get that boost, especially here at Earth where you're traveling, 400 meters per second if you're at the equator. That's a lot less fuel, a lot smaller rockets. But we have taken and compared the two amounts of energy. This is not all I want to talk about. This is just part one. That when we deal with an orbit, there's a certain amount of energy associated with the orbit. And that energy is going to be the gravitational potential energy and the kinetic energy. But it will always be negative because you are in orbit. If you had enough velocity to escape the orbit, then maybe we start getting to a value of energy that is 0 or positive. But as long as you're in orbit, you are trapped around the planet or the sun or whatever it is that you are orbiting. And because of that, your total potential energy relative to a place in space where the force on you is 0 is going to be negative. So objects in orbit have energy, and as we just discussed and just saw, that energy is a combination of their kinetic energy and their potential energy, or 1/2 mass of object v squared minus mass of planet, mass of object g over r. Total energy. They also have angular momentum. Right? It's an object traveling in a path around the star. We could calculate it like a point mass angular momentum, which would be r times mv times the sine of the angle between r and v. Or you could treat it as a point mass and do I omega. But since we often have v, usually it's easier to calculate the angular momentum that way. Now, this is obvious to a person like me, maybe less obvious to a person like you. But the object has a constant v and a constant r when it's in orbit. Circular orbit. So for a circular orbit, the energy and the momentum is constant for a circular orbit. However, it can be shown that even in an elliptical orbit, there is no external torque on the system. Because of that, all objects in stable orbits have a constant angular momentum and a constant amount of energy. All objects in a stable orbit have a constant angular momentum and a constant amount of energy. This is true for both elliptical orbits and circular orbits. So consider a planet going around a star. And let's put that planet at a variety of locations. Let's put a bunch of things together that we already know. We know from our prior conversations that the object's traveling the fastest here. That as it travels away, it's traveling too fast to be in a circular orbit. So it travels outside that circular orbit path. But the force of gravity begins slowing it down. Until it makes it over here, where it's traveling the absolute slowest. And of course, the direction of the force on the planet begins speeding it up again until it reaches that point where it's back at the start and it's traveling at its fastest. Consider looking at one of these. Say, how about this one? Oop, I don't want to do that. This one. This is R. It represents the torque arm, the distance from the pivot point to the object as it moves. And that green arrow represents V. The object's angular momentum here is going to be R times mv times sine of phi, where phi is this angle. That's the angular momentum there. Keep in mind, this will be the R over here. This is still V, and this is still phi. No matter where we are the object's value for r, the distance away from the pivot point, the object's velocity and angle are all changing all the time. But this is always a constant because there's no external torque. So the angular momentum for an object in orbit, even if it's an elliptical orbit, will always be a constant. In this case, though, the direction is an issue because v, phi, and r are all related. This becomes very challenging for us to calculate because it's hard to figure out the angle and the value for r for an ellipse. Even with the equation of an ellipse, you probably guys have been not taught how you figure out the distance from the focus to a point on an ellipse, have you? I never learned it when I was in school. Now you probably have some equation that's buried way in the back of your brain for what you could do to figure out where the foci are on an ellipse, and probably some other equation to tell you how to find the distance from both foci to a point on the edge. But then you would have to find the direction of the velocity tangent to that circuit, to that ellipse, to figure out what phi is. So although you may know those things, it's such a mathematically intense thing. We tend to not talk about it, except for two places. We do talk about it here and here. Is it obvious why? These are the only two places we tend to bring it up. And we'll call this R max and R min when we're at apogee and perigee, because here we're at V min and this is V max. At those two locations, the angle is 90 degrees. These represent R perpendicular MV. There's two of them. We tend to compare this location with this location because the angle doesn't factor into it because the angles at both of those locations are 90 degrees. So I just want to say that one more time. The thing I really want you to remember, no matter what the type of orbit is, all orbits conserve angular momentum and all orbits conserve energy. So the object has the same energy and the same angular momentum everywhere in its orbit. If you want to change orbits, you have to manipulate the energy and the angular momentum. That's it.